This is a recording of Chapter 2, Limits and Continuity, Section 4, on rates of change in tangent lines. I'll be using a combination of the notes here as well as notes that I will write out underneath the camera. To begin with, we just want to start with this definition of a slope of a curve at a point. The slope of a curve at a point y equals f of x at a point a comma f of a is the number m which equals the limit as h approaches 0 of f of a plus h minus f of a all over h. When you think of slope, hopefully you think of the difference quotient, the change in y over the change in x. Subtract the y coordinates over subtract the x coordinates. If you think about it, this is just the subtraction of the y coordinates of two different values being plugged into the f function. While the denominator is h, but h is going to represent this change in the x coordinate as well. I will give you a formal definition of this that you will see. Today we just want to practice using this limit notation. Before we do that, it's going to ask us about average rate of change over a given interval. When you think of average rate of change, I want you to think about distance, rate, time. And if I take a trip and I want to find my average rate of change for that trip, I'm going to take the total distance traveled divided by the total time. And that works for anything that changes over time. It doesn't have to be distance. It could be the change in profit over time. It could be the change in a particular disease over time. The average rate of change is found by taking the total change over the total time. So the first couple questions are going to be pretty easy. It's simply going to ask us to find the average rate of change over a particular interval. So let's do these two real quick. Average rate of change. It is important that you remember it's f at b. B is always the right endpoint of the closed interval over f at a all over b minus a. If I plug 3 in here, 3 cubed is 27 plus 1 is 28. If I plug 2 in here, 8 plus 1 is 9. 3 minus 2 is 1. So the average rate of change for this function over this interval is 19. This could be, let's say, a bicycle race. This is the total distance traveled in 1 hour. Therefore, the average rate of change is 19 over 1. But this works for any situation. Let's do this one. F at b minus f at a all over b minus a. You do have to be careful of this plus a positive situation. F at 1. If we plug 1 into the f machine, 1 cubed is 1, plus 1 is 2. Subtract. If we plug negative 1 in, look what we get. Negative 1 cubed is negative 1, plus 1 is 0. And we get 2 over 2 for an average rate of change of 1. Now, are the average rates of change always going to be these nice integer values like 19 and 1? No. Quite frequently, they're not. And that's why I just did a second quick example. But it's the same process. To find the average rate of change of f of x equals e to the x, it's exponential function. It's the same thing. F at b minus f at a all over b minus a. Just remember, b is the right endpoint of the closed interval. We can only find the average rate of change over closed intervals. Okay? This is plus a positive. If we plug 0 in, we get e to the 0 out. And if we plug negative 2 in, we get e to the negative second out. And 0 plus 2, we have 2 in the denominator. The key to this particular problem is that we will see e raised to the 0 frequently on the AP test. E raised to the 0 and cosine of 0. We need to know that both of those are 1. E raised to 0 is 1 because any base raised to an exponent of 0 is 1. And we've talked about that in class. And we know that the cosine of 0 is 1 because if you look at the unit circle, the x-coordinate of the unit circle at the angle of 0 is 1. And they're on there frequently because a lot of students will just make it 0. Those values are not 0. This is 1. At the same time, I'm going to rewrite this with a positive exponent, which is 1 over e squared, all over 2. Again, now it's a complex fraction. You can go from complex to non-complex in one step. The only denominator is e squared. That doesn't have a denominator. This doesn't have a denominator. It's 2 over 1. Look at each term, and the only denominator of these terms is e squared. So if I simply multiply each term by e squared, I can make this non-complex in one step. 1 times e squared is e squared. Negative 1 over e squared times e, it cancels. But don't forget to take 2 times e squared. Okay? And I know that's how Mr. Hearn did it last year in honors as well. If you want to make this all one fraction, and then flip, making sure that 2 stays on the bottom when you flip that denominator up, because right now it's 2 over 1. That's fine. You can do it in 2 steps. B. F at 3 minus f at 1 all over 3 minus 1. So f at b minus f at a all over b minus a. So if we plug 3 into this function, we get out e cubed. If we plug 1 into this function, we get out e to the first power all over 2. That's it. We leave it like that. You're going to be surprised how many times on the AP test you have an answer in terms of e or in terms of the sign of 3, and you just leave that. These are irrational solutions. E is an irrational number. We're going to get lots of irrational solutions. The majority of the problem set, though, will be of this variety when you're looking at the worksheet. At the indicated point, find the slope of the curve, an equation of the tangent line, equation of the normal line, and then graph the curve, tangent line, and normal line in the same viewing window. Okay, I'm going to start by finding the slope at the point down here. This is the most important part, so I'm just going to recopy this down here. We're doing it at x equals negative a. For the first problem, I'm going to write the generic form that I gave to you. The slope at a given value of a is found by taking the limit as h approaches 0 of f of a plus h minus f at a all over h. And again, this is just the difference quotient of the slope formula. I'll actually give you a nice proof of this so that you'll see what we're doing when we're taking this limit. We've been working hard on taking these limits. Notice if I plug in 0 right now, okay? If I plug in 0 for h, I get f at a minus f at a, which is 0 over 0. We know that the vast majority of the time when we get 0 over 0, when we're taking a limit, there is a limiting value. We just have to work to get this factor canceled out of the denominator. So how do we do it? Well, we use this function right here. It's probably best when you rewrite this to rewrite it using functional notation so that you recognize this is the machine that all of this is going into. When I plug something into the F machine, I have to square it. So here we go. The slope at A is the limit as h approaches 0 of. Take a plus h and plug it into the F machine. What comes out? A plus h squared. Minus, take a, plug it into the F machine. What comes out? A squared all over h. Now in this particular problem, we want to find the slope at negative 2. So we can plug negative 2 in for a right now. I didn't really have to show this step. Neither one of these steps do you have to show when they want you to find the slope at a particular value. This is our a value. So this could be your first step. I just wanted to show you how it's going in. And from here on out, I will just start by plugging in the negative, or this negative 2, or whatever this a value is, in for a right away. Negative 2 plus h squared minus negative 2 squared all over h. But I have to FOIL this out. The key is I have to get this h canceled out of the denominator. So for lack of anything better to do mathematically, let's at least just multiply everything out in the numerator, and hopefully we will get some of the terms to cancel. Negative 2 times negative 2 is 4 when I multiply the first. The outer is negative 2h, the inner is negative 2h, so that's a negative 4h. Don't forget the outer and the inner because we are FOILing. Plus last times last is h squared. A negative 2 squared is 4. And look what happens. Now I know this is going to be tempting, that you're going to want to cancel terms and factors in the same step, but please don't. That factor, those terms cancel, and now I can factor out an h out of both terms. I don't want to see you cancel part of the addition or part of the subtraction. That can lead to bad habits mathematically. I have to rewrite it anyways to cancel it, because you can't cancel terms and factors in the same step. So why not factor this greatest common factor of h out front? Because now this is more algebraically sound to show that we are canceling this factor. The slope at negative 2 of this particular function I can find by taking the limit now. Now that h is out of the bottom, and that's always going to be key to these problems, is to get the h canceled from the denominator. When you plug 0 in, negative 4 plus 0 is negative 4. So the slope of this curve at negative 2 is negative 4. That's the hardest part of this particular problem, but this is one of the easier problems of this variety because it's a pretty easy function to start with, just this x squared. So I'm going to write it up here. The slope at negative 2 we know is negative 4. It asked me to graph the function, a tangent line, and a normal line at this value. Okay? Let's just start by graphing this. If you plug 0 in, you get 0 out. If you plug 1 in, you get 1 out. If you plug 2 in, you get 4 out. If you plug 3 in, you get 9 out. It's a mirror image over here. It's a nice even function. Plug negative 2 in, 1, 2, 3, 4. Okay. 3, negative 9, and we graph this nice parabola here. Now I am using a pencil to graph this, and it may be a little bit harder to see, but I want to keep the graph fairly thin because now I have to graph a tangent line to this graph at this point right here. In other words, when I plugged in negative 2, because that's my x-coordinate, the point of tangency, I always get the y-coordinate of the point of tangency by just plugging the x-coordinate into the original function, and negative 2 squared is 4. That is my point of tangency. So if I want to find the equation of the tangent line, I have a slope and I have a point that it passes through. To find the equation of a tangent line, write it in linearization form first. Y equals the y-coordinate plus the slope, since it's a negative 4, I'll just say minus 4, times x minus the x-coordinate. X minus negative 2 becomes x plus 2. If it was a free response question on the AP test, we would leave that. But if we want to graph it, we like it in slope-intercept form. Well, now it's an easy, really one step. Negative 4 times x is negative 4x. Negative 4 times positive 2 is negative 8. Negative 8 plus 4 is a negative 4. That is the equation of the tangent line. This is the tangent line. And we can actually graph it. We know we want it to be tangent at this point. If I count the slope, I'm going down 1, 2, 3, 4 over 1. I'm going up 1, 2, 3, 4, back 1. And if I connect these, right through that one point. A tangent line means that it just barely glazes that. Okay? And if I look at this line, the y-intercept is supposed to be 1, 2, 3, 4. Yeah. It's going through -4. Normal line. When we're talking about the normal line, what I want you to think about with the normal line is perpendicular. It means find the line that's perpendicular to the tangent line. So here is the normal line work. It's the exact same process, except the slope of the perpendicular, upside down capital T there, that's symbol for perpendicular, we have to take the opposite reciprocal. So take the reciprocal, -1/4, and change the sign as +1/4. The point of normalcy is always going to be the same point as the point of tangency. We don't have to change anything there. It's still going to go through that same point. We do the exact same thing. Y equals the y coordinate. This time it is plus the slope times x minus the x coordinate. X minus -2 becomes x plus 2. And I still think you should be able to convert the slope-intercept then in one step. 1/4 times x is 1/4 x. 1/4 times 2 is a half. 1/2 plus 4 is 4 1/2. Now I want to keep in mind that it's 4 1/2, but we don't like mixed numbers when we're writing fractions. So 4 1/2 is the same as 9/2. The reason we don't like mixed numbers is because if our slope was an improper fraction, we would leave it as an improper fraction, not a mixed number, because it's rise over run. And just to have that consistency, we always want to write, when we're talking about equations of lines, we want to write it as an improper fraction as opposed to a mixed number. That's how you're going to see it the vast majority of the time. Well, can we graph this one? I'll graph this one in purple. It still goes through the same point. But now we're going up 1 over 1, 2, 3, 4. Up 1 over 1, 2, 3, 4. Up 1 over 1, 2, 3, 4. You can count out as many as you want to, okay? But make sure that you draw it using a nice straight edge. Especially me, because I'm not great at drawing nice straight lines. There it is. And we ask ourselves, is this perpendicular here? Yeah, that looks perpendicular. The tangent line and the normal line should be perpendicular. The y-intercept was 4 1/2. Does it look like the y-intercept of this line is 4 1/2? Yes. Good. So now let's take a look at a more complex situation, simply because we're dealing with a rational function now instead of a nice, simple y equals x squared function, parabolic function. So I'm going to write it down here. The f function, f of x, is 1 over x minus 1. And I want to find the slope at x equals +2 in this particular problem. So I'm not going to write down the generic formula again. I'm not going to write it down with a in there. I'm going to substitute 2 in for a, and I'm going to go right to this. The slope at 2 is the limit as h approaches 0 of f of 2 plus h minus f at 2 all over h. And I can find the slope of this rational. This is a rational curve. Okay? I can find the slope, the instantaneous rate of change of this curve when x equals 2. We just have to plug all of this through. Notice again, if I plug in 0, I get f at 2 minus f at 2, which is 0 over 0. The vast majority of time we have a limit. We just have to find it. And you're going to see a lot of the same limits as you go through this process that you saw in previous sections. I think this is a problem that we saw in previous sections. But I've got to take 2 plus h and plug it in right here. Minus f at 2 plugged in right here, all over h. All right, so if I plug in 2 plus h, it's going to be 1 over, notice, 2 plus h minus 1. Well, 2 minus 1 is 1 plus h comes out. Subtract f at 2. Well, look what happens. If 2 comes in, 1 over 1 is just 1 all over h. You can make this all one fraction and multiply by the reciprocal if you want to take a couple steps to do it. Multiplying this by 1 plus h over 1 plus h. But the better you get at doing this in one step, it's going to save you some writing. I'm just trying to save you some writing from what you had to do in your Algebra 2 class. And I know Mr. Hearn simplified complex fractions this way as well. If it helps, write this like over 1 over 1. So I'm looking at all of the denominators, both in the numerator and the denominator of my complex fraction. The lowest common denominator of all my denominators of those terms is 1 plus h. It's the only denominator that we have. I need to multiply all of these by that lowest common denominator, because that's the same as multiplying the top of the complex fraction by 1 plus h over 1 plus h. And you don't have to show that. I'm multiplying every term by 1 plus h. The 1 plus h cancels. I'm left with a 1 minus 1 times 1 plus h, because I have to multiply that by 1, and I have to multiply the h by 1 plus h. Complex to non-complex in one step. It's going to save you a lot of writing on these rational functions. Because now I want to distribute the 1, negative 1. Don't forget to distribute the negative sign. Never cancel terms and factors in the same step. But I can cancel the term of negative 1. And it's tempting. You want to just cancel this thing. Always write the limit notation down until you actually take the limit. So there's enough extra writing that I'm making you do without having to do the extra writing on simplifying a complex fraction. Cancel the h. This is negative 1 over 1 plus h. Now that h is canceled from the denominator, that's the key. Now I can take the limit. When I plug 0 in, 1 plus 0 is 1. Negative 1 over 1 is a slope of negative 1. There it is. Now let's go back up and do the graphing part and find the equation of the tangent line. You're going to find lots of equations of tangent lines throughout the year. First semester, we do it in almost every section from here on out. Find the equation of tangent lines. So the slope at 2 is negative 1. I'm going to rewrite that up here. The slope at 2 is negative 1. The point of tangent C. You always find the point of tangent C by plugging the x-coordinate into the original function. 2 minus 1 is it's a point 2, 1. As a matter of fact, if we want to graph this situation, and maybe I'll wait to graph this one, let's just find the equation of the tangent line first. Y equals the y-coordinate plus the slope. This time I'll just put minus 1 times x minus the x-coordinate. We would leave it like that on a free response, but since I have to graph it, I want to convert it to slope-intercept form. Negative x plus 2 plus 1 looks like negative x plus 3. And again, it's good to say this is the tangent line. So we know which one's the tangent, which one's the normal. Because now we need to find the normal line. The normal line. The only difference is I have to take the opposite reciprocal of the slope. So the slope of the perpendicular is going to be positive 1. Point of normalcy is going to be the same as the point of tangency. It's still the point 2, 1. Y equals the y-coordinate, which is 1, plus the slope times x minus the x-coordinate. So 1 times x minus 2 is x minus 2, plus 1 is x minus 1. This is the normal line. So let's graph everything here. Remember this rational function. If I'm going to graph this rational function right here, it has a vertical asymptote at x equals 1 because 1 makes a 0 in the denominator and we cannot divide by 0. It is a pole because it's x minus 1 to the first power. The degree in the numerator is less than the degree in the denominator, so y equals 0 is the horizontal asymptote. And really, if you just plug in 1 point, as a matter of fact, if you plug in 2, you get out 1. We've already done that. So this point right here, and we can graph this situation knowing that we're going to approach the vertical asymptote this way, and we're going to approach the horizontal asymptote this way. This is a pole, so we slide down again. But if you want to plug 0 in, you get negative 1 out. We've graphed this function a number of times. Here it is. There we go. Okay. Now it wants us to graph the tangent line. That means it's just going to barely graze that point, the point 2, 1. As a matter of fact, I've already found the equation of the tangent line right here. I will graph this one in purple. So if I just start at this point, the point of tangency, if I go down 1 over 1, down 1 over 1, up 1, back 1. Oh, look at it. The y-intercept is 3. Yep, that's what it's supposed to be. It's supposed to have a y-intercept of 3. Use a straight edge on these so that we have nice, accurate tangent lines. Okay? The rate of change of the curve is the same as the slope of the tangent line. They're one and the same. I'll do the normal line in blue. Down 1, back 1, down 1, back 1, down 1, back 1. And if I draw that in, 2 things that we should notice. These lines look perpendicular. That's good. They're supposed to be. And the y-intercept of the normal line is negative 1. That's what it's supposed to be. Next problem. I'm not sure if I put these on the worksheet or not, but I do want you to know, I know some of you have learned how to take derivatives with Mr. Hearn, but understand right now you have to use the slope definition to indicate the slope. Okay? I'm interested only in this limit definition of a slope, not your derivative rules. We will get to that. That will make this process way easier. I get it. So on this one, it says determine whether the curve has a tangent line at the indicated point. If it does, give it slope. If not, explain why not. One of the first things that we need to do is check to make sure that this is continuous, because we cannot have a slope at an interior point if we do not have continuity. How do we check continuity? The limit as x approaches 0 from the left of this function, does that equal the limit as x approaches 0 from the right of this function? And does that equal f at 0? You have to check this too, because maybe it's not defined at 0. But to check the left-hand limit at 0, I just plug 0 into the top equation, I get out 2. If I plug in 0 into the bottom equation, I get out 2. And 0 is defined by the bottom equation, so yes, they are all equal. Therefore, f of x is continuous at x equals 0. So now, if the slope exists, I have to check to see if the slope from the left equals the slope from the right. And we have to check it using this slope definition, this limit definition for slope. So on this part, the left-hand side is this function that I'm going to use, 2 minus 2x minus x squared. On the right-hand side is 2x plus 2. I'm just checking the slope from the left versus the slope from the right. In both cases, I'm going to use an a value of 0 because I'm checking it when x equals 0. Okay, so that's going to be my a value. So let's start with this one. It's more complex. And here's how you're going to indicate it. The slope at 0 from the left of this function equals the limit as h approaches 0 of f of 0 plus h minus f at 0 all over h. Zero plus h is just h. And if I plug h into my f machine, here's what I get out. 2 minus 2h minus h squared. Minus f at 0. If I plug 0 in, that goes to 0, that goes to 0. I'm just subtracting 2 all over h. I have to remember to keep my limit notation until I take my limit. Never cancel terms and factors in the same step. There it is. The slope at 0 from the left is the limit as h approaches 0. I'll go ahead and factor out the h because I know that's the key to this problem, is being able to cancel the denominator that has an h in it. Now I'm not going to have 0 divided by 0 anymore. Once I get that factor canceled, there's no more division by 0 error when I use substitution to find this limit. The denominator is just 1. And if I plug 0 in, negative 2 divided by 0 is negative 2. Okay? But now I got to check the slope of this function at 0 from the right. Now, a lot of you are going to look at this and say, well, clearly the slope is 2. It's linear. I still want you to plug it through. I could give you more complex problems. I'm going to give you nice things that you should know that, yes, the slope is 2, but I still want you to verify it using this limit notation, this limit definition of slope. Again, f at 0 plus h minus f at 0 all over h. This problem is made significantly easier because the breaking point is at 0. And that's not always going to be the case. Okay? So the limit as h approaches 0. Because 0 plus h is just h, so I plug h into here. I get 2h plus 2 minus f at 0. Plug 0 in. I get subtract 2 all over h. Cancel. The slope at 0 from the right is the limit as h approaches 0 of 2h over 2. I'm sorry, 2h over h. Okay? And I cancel the h. And I'm left with the slope at 0 from the right is the limit as h approaches 0 of 2. The limit as the variable approaches any number of a constant is always just a constant. And that's what we should have gotten, right? The slope from the right is going to be positive 2. Clearly, it's a line. It has a slope of 2. It always has a slope of 2. So the question really asked, does this function have a slope at 0? And the answer in this is no. Just like it was with limits. We would say no. Since the slope at 0 from the left does not equal the slope at 0 from the right. The slope at 0 from the left does not equal the slope at 0 from the right. Negative 2 does not equal positive 2. So although this is a nice continuous function. It is not a situation where the slope is going to exist at this breaking point between this parabola and the line. It turns out it's too sharp. It's too sharp of a point to have a definitive slope at that point. Follow along with the same idea. The only difference now on these particular problems is that we're not finding the slope at a numerical value of, let's say, 1 or 2 or 0 like we were doing. We're just going to find the slope at any constant value x equals a. It's just an arbitrary constant. We do the exact same thing that we've been doing. The slope at a is the limit as h approaches 0 of f of a plus h minus f at a all over h. This is just going to be more abstract. Slope at a is the limit as h approaches 0 of. If I take a plus h and plug it in right here, a plus h quantity squared plus 2, put brackets around that, minus f at a. So I always separate the front and the back functions with brackets. So I remember I have to multiply this out and then add 2. Okay? So here it is. We got to FOIL this out. The limit as h approaches 0. When I FOIL this, first is a squared. Outer is ah, inner is ah. That is 2ah plus h squared plus 2. I might as well distribute the negative sign, minus a squared minus 2 all over h. This seems like it's getting worse, not better. But if you plug 0 in for h, you're going to end up getting 0 over 0 still. We have to get this h gone. Every term that doesn't have an h in the numerator will cancel every time. If you multiply it out correctly, every term that doesn't have an h will cancel. So that we can then factor out a greatest common factor of h. If we factor h out front of the two terms that are left, we get a 2a plus h all over h. Factoring out the greatest common factor of h out of these two terms. And then I cancel the factor of h. This is the limit as h approaches 0 of 2a plus h. The bottom's just 1 if you want to write that, but you don't have to, just 2a plus h. Now I can plug 0 in because I don't get a division by 0 error. If I plug 0 in for h, I get out 2a. Think about what this tells us now. This is very important. If I want to find the slope of this curve right here at any value of x, so a could be 2, it could be 3, it could be 5, it could be negative 0.5. It's just simply going to be 2 times whatever the x-coordinate is. That will tell me the slope. So now I have this nice generic formula that will give me the slope at any value of a. So if I want to know the slope at a variety of different values, maybe at 2, at 4, at I don't have to go through this every single time. I can just plug whatever the a value is into here. Think how useful that would be. Let's take a look at one more of these. It's really the same one that we just did. We're just going to leave it abstract, but I want you to see one of these rationals. Start the same way. The slope at a is going to be the limit as h approaches 0 of f at a plus h minus f at a all over h. This was going to get complex because it's a rational. Every time we're cranking a rational function through this limit definition of a slope, you're going to get a complex fraction. In this one now, I get 1 over a plus h minus 1. Subtract 1 over a minus 1 all over h. If it helps you, write this as h over 1. What is my lowest common denominator of all the terms in the numerator and the denominator? I'll write it up here. I'll write it right here for you. The lowest common denominator is going to be a 3-term factor a plus h minus 1 and a 2-term factor a minus 1. Those are the only denominators I have, but this denominator is completely different from this denominator. But watch, complex to non-complex in one step. Multiply all 3 parts of this by my lowest common denominator. The slope at a is the limit as h approaches 0. If I multiply this fraction by the a plus h minus 1 cancels. I just have 1 times a minus 1, so it's a minus 1. Subtract. If I multiply this fraction by this, the a minus 1 cancels. And I'm left with a plus h minus 1. But I have to remember to multiply h by a plus h minus 1. I'm going to write the a minus 1 first, and then the a plus h minus 1 second. Doesn't matter what order we multiply in. Whew! If I plug in 0, I still get 0 over 0. I have to get that h canceled out of the denominator. A minus 1 minus a minus h plus 1. H times a minus 1 times a plus h minus 1. Every term in the numerator that does not have an h must cancel. A cancels with negative a. Negative 1 cancels with positive 1. So that every term that's left in the numerator must have an h. They all work out the same way. Look at that. Cancel the factor of h. Never cancel terms and factors in the same step. So it's negative 1 on top, a minus 1 times a plus h minus 1. Now I'm ready to actually take the limit by plugging in 0 for h. I get a negative 1 on top and a minus 1 times a minus 1. A minus 1 times a minus 1 is a minus 1 squared. That is the generic slope formula for this curve, and we're actually going to be able to find this later on doing what you did last year using the quotient rule. But this is where all that stuff comes from, is from using this limit definition.